I'd like to take a moment to introduce you to our speakers. Jason Lin is Senior Vice President of Forecast Services for WDT. Jason has extensive knowledge of forecasting tropical storms and short-term hazardous events. Many very large trading floors have utilized Jason's forecasting skills during tropical events, severe weather events, and cold outbreaks. He is one of the few accomplished operational GSEM practitioners in the meteorological community. Jason has an MS in meteorology and more than 8 years of combined experience at the National Severe Storms Laboratory and the Storm Prediction Center. He has also handled extensive asset protection responsibilities for 2 significant energy companies in 5 of his 11 years in the energy space. Ed Berry is Senior Scientist and Forecaster for WDT. He has an MS in meteorology and over 30 years of professional experience, including serving as a Science Operations Officer as part of his more than 20-year tenure with the NWS. Ed is a highly skilled long-range and seasonal forecaster, especially for events involving tropical mid-latitude interactions. He was awarded the National Oceanic and Atmospheric Administration's Bronze Medal for issuing the first highly skilled, physically based forecast of weather and climate hazards in the global tropics. In addition, Ed received a Special Act Service Award for the creation of a specialized climate training program and has authored many articles on synoptic global scale linkages. After Jason and Ed's presentations, we'll be hearing from Claudia Dent, Vice President of Product Management at Everbridge. Claudia has many years of experience in the technology industry and has held executive positions in product management, marketing, business development, and general management at companies ranging from startups to large global enterprises. And we're excited and honored to have all of our speakers with us today. So now I'd like to turn it over to our first presenter, Jason Lin. Jason, you may begin.
Thanks, Erin. It's worth noting, following that introduction, it was mentioned that I'm a GSDM practitioner within the meteorological community. I'd like to point out that Ed Berry is one of the co-founders of the GSDM framework, and we'll give you a peek at that advanced forecast framework and list of methodologies and exposure to some of the techniques later in the presentation. With that, I'll get started. Good day, everyone. Many of you are probably thinking that intro for Jason and Ed mentioned the tropics quite a bit. What the heck could the tropics have to do with winter weather? I promise you we'll illustrate some of the connection, especially in Ed's portion of the webinar, but I do want to give you at least a brief tease. Highly anomalous weather events and large buckles in the jet stream are often the result of interaction between the tropics and mid-latitude weather features. But I'll save the rest of the illustration of the connection for Ed's very informative portion of this upcoming presentation. Severe thunderstorms and tropical cyclones are not the only weather phenomena that are disruptive to commercial activity and downright dangerous to the general public. High-impact winter weather events such as major Arctic outbreaks, intense snowstorms, and major ice storms can have numerous similar adverse effects, often with larger geographic coverage than the more focused hazards presented by a large springtime convective severe weather outbreak. Thus, the winter hazards are potentially more broad-based in delivering adverse economic impacts without possessing the similar, I guess, acute lethality a series of tornadic supercell thunderstorms could pose. I'd like to start today's presentation with a simple review of some of the primary winter weather hazards associated with high-impact winter storms within the context of some of their related meteorological concepts. Major winter storms actually have much more in common with tropical cyclones, being synoptic to mesoscale features, than they have in common with clusters of severe thunderstorms, for instance, whose hazards are more sub-mesoscale features. The size and intensity levels of both major winter storms and tropical cyclones are strongly governed by the background hemispheric to synoptic pattern evolution. Both phenomena are essentially ingredients-based, smaller scale results of the interplay among processes at differing time and space scales. The ingredients-based approach for a tropical cyclone forecast can be oversimplified to include pre-existing source of vorticity or spin at low levels, often provided by a tropical wave, access to ample deep layer moisture in the presence of a conditionally unstable vertical atmospheric profile bearing light vertical wind shear. A bit complicated list for the non-meteorologist, but very easy to define in our line of work. These conditions are brought about through preferred undulations and interactions of the mid-latitude and tropical latitude flow. The ingredients-based approach for a high-impact winter storm, for instance, can be oversimplified as the need for large-scale forcing for ascent, upward motion, relatively low static stability, or the ease with which air can be lifted. Got to have access to ample moisture, got to have access to deep layer cold air. All of these ingredients, the presence of them, are driven by the pattern evolution. And thus, sensible weather hazards can be generated by the larger scale pattern. That's the whole take-home message there. Highlighting some of these hazards, this first slide shows what would be a general schematic cross-section cutting vertically through the east side of a developing major winter storm, from south on the left side going to north on the right. The ingredients, some of the ingredients I just previously mentioned, now can be seen at work, generating varying types of precipitation, which is the obvious first winter hazard we can discuss. Forcing for ascent is present via warm air transport northward from left to right up the sloping frontal surface, and in this case the front is a slowly retreating warm front or stationary front. And this upward motion occurs in the warm air transport atop the low-level cold air at the surface. We'll also see presence of mid and upper-level forcing for ascent related to other dynamical processes, which I won't go into, like vorticity advection or interaction with nearby jet streaks. The precipitation types at either end of the cross-section are pretty easy and rather straightforward. On the far left, precip falling through a deep layer of above freezing air equals rain. On the far right, precip falling through a deep column of sub-freezing air yields snow. The amount of snow is proportional to the intensity of moisture transport into the cold column, along with the ease with which the air can be lifted, or some measure of the static stability, and the efficiency of ice crystal growth, with higher crystal growth rates occurring generally in the layers of -8 to -12 C aloft. Snow rates can exceed 3 inches per hour in some of these more intense winter storms, when all of these ingredients are at extremely favorable levels. Precip type becomes much harder to handle in the region of the quote-unquote elevated warm nose, when the warm conveyor belt segment of the flow rides atop the low-level freezing air beneath the zone where precip is produced, which is pretty much the middle portion of this schematic. The warm nose melts initially frozen precip with the resultant surface phase dependent on the depth of the low-level cold layer. If you have deep enough and cold enough air to refreeze the airborne precip particle, you get sleet, which can still accumulate to damaging levels since this zone can be particularly efficient in precip production. If the subfreezing layer is too shallow to refreeze the airborne particles, but is cold enough to maintain surface skin temperatures well below freezing, the rain can refreeze and crystallize on contact, building up layers of ice, which can be very devastating to transportation and utility infrastructure, which can have crippling effects over rather large regions. When we talk about mitigation of these hazards, mitigation of precipitation hazards is rather difficult. One can limit or cancel travel plans when periods of heavy snow rates or ice glazing are forecasted within the coming 12 hours, or you can maybe use a longer lead time for longer travel plans if you're planning a interstate trip. The other dangers of frozen precip, of course, is accumulation onto objects like trees, which can break under the weight of the accumulation. So trimming excessive tree growth around power lines leading to your home or to your office is probably a good idea heading into winter, especially in regions that are prone to having significant winter storms. You may need to make a request to your local power provider in order to address that issue. You can also have excessive snow accumulation removed from roofing to limit structural risk, it's probably a good idea to start taking snowpack off the roof when the pack depth exceeds 6 to 12 inches. Of course, this can depend on the quality of the construction, though, as well. Let's go to the next slide, please, Ed. The cold air itself can present a hazard in its own right, threatening the human body's ability to maintain a healthy tissue temperature for the exposed extremities. Or, worse yet, for prolonged exposure, the cold air can counteract the body's ability to maintain a critical core temperature. Please be mindful of the additive effects of the wind as it evects heat and moisture away from the body. The wind chill chart shown in this the second slide illustrates just how quickly exposed skin can face effective temps in the -30s Fahrenheit with winds roughly in the 30 to 40 mile per hour range and temps in the single digits. And these parameter values are quite a common occurrence on the northwest and western quadrants of major winter storms, which tap Arctic origin air and bring it down into the Rockies, the Plains, the Midwest, and the northeastern sections of the U.S. Notice on the chart, frostbite can occur in about 10 minutes in these conditions. And hypothermia becomes an issue when the core body temperature falls below 95 degrees. And with these types of weather conditions, that can occur in less than 25 minutes if one is caught out in one of these storms unsheltered. The cold air can also wreak havoc on exposed pipes, of course, that contain residual water. When temps drop below about the low 20s Fahrenheit, as many unfortunate owners of sprinkler systems in the southern third of the nation can unfortunately discover during rapidly evolving Arctic outbreaks that send the Arctic front all the way to the Gulf. Mitigation of the threat of cold air exposure is quite a bit more straightforward than fighting off precip hazards. Simply be aware of the wind chill level. Limit your time outside. Bundle up in layers of clothing to efficiently insulate yourself. With wind chill levels in or below the -30s Fahrenheit, just plain don't go outside unless you must. Cover exposed pipes with insulation. Local hardware stores can be very helpful with this mitigating aspect. It's probably a good idea to drain and winterize sprinkler systems unless you want to roll the dice against an Arctic outbreak all winter long. Next slide, please, Ed. In the meteorological community, we can use historical analysis to construct a classic composite of a major winter storm, shown on this particular slide. Applying this general conceptual model and being aware of one's location relative to the important composite features like the warm fronts, the cold fronts, the surface low pressure center, and the mid-level low pressure center, often referred to in the forecast, even by TV meteorologists. Knowing your location relative to these features can be very useful information in preparing for the effects of one of these major winter storms. Recall, a high-impact winter storm is generally governed by the pattern evolution, and this pattern evolution serves to co-locate the necessary ingredients, most of which can be seen at work on this composite. Note the implied highly amplified nature of the pattern, likely related to a very large ridge building north through the western portion of North America into western and northwestern Canada. Oftentimes they'll have quite mild conditions up in the western part of North America, while the eastern two-thirds of the U.S. can drop into the icebox. And this big ridge up into the western part of North America displaces Arctic origin air. It generates surface high pressure, which can drive the cold air southeast or south-southeast into the U.S., delivering some of the key winter storm ingredients onto the scene, which we've talked about: the deep layer cold air and the forcing for ascent on the east side of the digging trough, where you see the enclosed scalloped regions, implying cloud cover, precipitation generation, and rising motion. The amplified pattern also taps warm, moist air from the subtropical and tropical latitudes, feeding into the storm on the warm conveyor, represented by that red arrow. And this supplies the other primary winter storm ingredients that we mentioned earlier, the moisture transport and contributes to the lower static stability, the greater ease with which the air can be lifted. Also recall the cross-section of precip types through the eastern side of the storm from my first slide. The ice threat generally occurs just on the north side of the warm front, while the heaviest snow risk occurs farther north of the warm front, stretching back generally westward along the path of the mid-level trough, near and just to the north or northwest of the surface low pressure track. So paying attention to the forecast of these features can improve your situational awareness and allow for more effective preparation. Having mentioned the importance of the pattern evolution in driving these high impact events with providing the ingredients, I now have a pretty good segue to pass the controls over to my very esteemed colleague, Mr. Ed Berry, to discuss some aspects of pattern forecasting, including a peek at a portion of last winter that can illustrate some of these points. Go ahead, Ed.
Thank you very much, Jason. That was certainly an excellent review of what folks need to be careful about, especially in portions of, at least for the U.S., where winter is definitely an issue as we go forward for the rest of this year into early next year. Okay, my part here is it's a bit of a gear shift too. It's starting to look more at the scientific aspects, but I want to do so in a high-level way. First of all, a framework that my research partner and myself have been doing for many years, Klaus Weichmann, who just retired from working at the Environmental Systems Research Laboratory in Boulder. And we've, over the years, as I just said, we constructed this weather climate linkage framework known as a Global Synoptic Dynamic Model for Subseasonal Atmospheric Variability. And one of its purposes is to monitor on a daily basis just what's going on in terms of the circulation state. And this daily monitoring is sometimes critical to catch high-impact weather events, including cold outbreaks. And in the remainder of this talk, it's essentially going to be three aspects, maybe four, depending on how you want to number that I'll be talking about. And as Jason said, first I'll be reviewing a situation we had during March of earlier this year, March of 2013, for the cold that dominated much of the central and eastern U.S. Then talk a little bit about the weather climate state since then, and then finally how that may give us some information of what we can expect for the winter of 2013-14. And during this whole presentation, I'll be showing just from a very high level point of view some of the tools we use as part of our GSDM framework. Okay. Going into March of earlier this year, say from late January into early February, as people were starting to project forward, there was a consensus out there, as I remember, that March of 2013 would essentially begin quite warm, especially for the central and eastern U.S. Now, this slide that you're looking at here is a forecast made from the European Center for Medium-Range Weather Forecasts for 2-meter air temperature anomalies. And, you can see the scale at the bottom, and I can't describe every detail, especially for the more complicated figures that I'll be getting to. But the point here is that there was a prediction of warmth east of the Rockies with about roughly a 3 to 4 week lead time going into about the first week or so of March. That's the takeaway there. And other models are also doing the same type of prediction. This is from the climate forecast systems that's generated from the National Center for Environmental Prediction in Washington, D.C. Regardless of some of the differences in the spatial patterns of temperature anomalies, the point here is it's cold in the western U.S. and a general warm signal over the central and eastern part of the country. Now, those two forecasts I just showed were made roughly about the first couple of weeks going into February, and specifically February 11th, initial conditions. Okay, about 10 days later, just showing the sequence here from the climate forecast systems predictions, even about 8 or 9 days before the beginning of March, again, we still have this forecast of cooler west, anomalously below normal temperatures in the western U.S., warmth in the east, and as you can see, by the time we get to the last day of February, the forecast is essentially reversed. In other words, this is an example where even a coupled model that's designed for seasonal forecasting is just catching on to rapidly changing initial conditions in the circulation. In other words, at least from a numerical modeling point of view, the situation that happened as far as the anomalous cold, as you see in this lower right, this is what verified. What you're looking at here are tercile, that is 3 categories of below, near, and above temperature anomalies. What happened and what was forecast, even with as little as a 5 to 10 day lead time, were 2 different things, attesting to essentially the low predictability of the situation that occurred in March. However, myself and a few other colleagues monitoring the circulation state during this period were able to catch that March was not going to come out, was not going to start out warm, and may not end up being warm with about a 2-week lead time. And I'll try to show you a few reasons how we were able to get that. So let's go forward here. This is where we start getting into some of the more, some of the details. And you know, I'll take questions, you know, either online or offline as to just what some of these plots are and where you can go find them and so forth. Because obviously time won't allow me to go into this in depth. But you're looking at a time section here of anomalies of outgoing long-wave radiation in the near equatorial region, 7.5 south to north. And what you're looking at are just whether there are deep cloud layers producing heavy precipitation in the tropics, or whether the skies are clear and sunny. These colder colors here, these blue colors, are areas of heavy precipitation, whereas the warm colors are where things are suppressed. And this is actually for the last 2 years, and all I want you to see here for the time being is that there is variability that occurs in slower time scales of these envelopes of these rainfall patterns in the tropics. You have these slow things going on here, as I show with this red arrow. Then you have some of this faster stuff going on. There's multiple time scales occurring, and it's this interaction, the superposition of multiple time scales is one thing we try to capture as we do our weather climate monitoring every day. What happened about a year ago, a little over a year ago, is that we actually had a warming over the western Pacific Ocean, and this allows some of these deep tropical thunderstorm clusters to come out into the West Pacific. And to keep a long story short, that had an impact of what happened this past March. And I think what I'll do is just leave it there and move on. And keeping in mind what I just quickly showed in terms of the variations of tropical rainfall, we not only monitor these tropical rainfall variations, but also just what the global and other aspects of the circulation are doing as well. One of the key components of this global synoptic dynamic model, and it's actually the dynamical underpinning of it, is looking at the Earth atmosphere angular momentum budget. Well, all we're saying with angular momentum is that we're just trying to get some quantitative measure as to how the winds are blowing, are behaving, how the circulation is behaving, both in terms of its global variations, as well in various latitude bands, both north and south of the equator. That's why I wrote it, why I have it labeled at the top left here. Just in a sense, we're just monitoring the behavior of the jet stream on a global scale. Both in the extratropics as well as in the tropics itself. There are jet streams in the tropics, but they're a little bit different than outside the tropics. There's a lot of stuff going on here, as you see when we start looking at how this global behavior that you're seeing in the bottom time series, where it's getting its contribution from various latitudinal bands, both north and south of the equator. And if you look a little closer, regardless of the details of the cold colors and the warm colors and things like that, you can see roughly on the order of maybe 30 to 60 day regimes. We had like about 5 of those as we came out of the summer of 2012, heading into this past winter, and going into March of this past year, we had something occur in November and December, and then a change occur from December into early February, and then another change occurred during February itself, leading to the situation we had in March. And something else that I want to point out here, besides looking at the variation of the global mean and zonal mean wind patterns, occasionally we do get feedbacks from the stratosphere, and that's one of the things that we also try to stay on top of with our framework. Is not only do we have forces occurring in the atmosphere that are causing some at times rather complicated variations of jet stream patterns, but we also get feedbacks from them, and one of those areas of feedbacks can come from the stratosphere, because the troposphere is what actually forces the stratosphere. It's not the other way around, but you can get feedbacks from a stratospheric, in this case, a sudden stratospheric warming, which is what happened in January. And that's what this next slide shows you here. We had this rapid warming, and it was sudden. That's why it's called a sudden stratospheric warming. This wave energy propagates down into the upper troposphere, and the result was anomalous high pressure at the polar latitudes. And some people like to develop these indices, and some people like to call them teleconnections and things like that. And that's all fine, but the way I look at things is not in terms of indices, but in terms of the patterns themselves and the dynamics that are forcing those patterns, and how you can extract information from the dynamics that are forcing those patterns to make a forecast. In the case of March, we had possibly the lowest value of the Arctic Oscillation, a strong negative phase of the Arctic Oscillation, meaning strong high pressure at the polar latitudes, perhaps on record from the Prediction Center. And I think their values go back to 1948. At least that's when they were able to start doing their computation. Of course, there's data issues and things like that as well. But anyway, there was impact from the stratosphere, as well as other aspects involving tropical forcing and the circulation itself that I just quickly went through. And so how did all this complex interaction manifest itself in terms of synoptic details, both on the slow and fast time scales? Well, that's what I'm showing here in terms of these hemispheric plots. What you're looking at here are 500 millibar height anomalies for stereographic projections for December, January, and February. And this is a seasonal mean right here for DJF. Now, one thing you can see right away is that you go ahead and average these three panels here. You can get a seasonal mean that suggests a ridge over the Central Pacific in some form of a trough, at least in terms of negative height anomalies over the western U.S. with a downstream ridge. But there was clearly quite a bit of circulation variability going on, and that circulation variability was being driven by some rather complicated, let's just say, circulation dynamics that I only just briefly touched upon. But nevertheless, there was this slow, simple evolution of strengthening westerly flow in the subtropics, starting to emanate from East Asia during December, continue to shift east across the Pacific to the southwestern U.S. during January, and finally, these westerlies broke through across the U.S. during February. Now, synoptically, this manifests itself as a southward shifted jet, and the storm track across the U.S. at that time became quite active. And I think there were at least 2 or 3 significant snowstorms that occurred across the central U.S. And for example, and I have to go back and look at this because there's just too many data points in my head, but Kansas City, Missouri may have had one of the snowiest Februarys on record. But in any case, we look at all these complex behaviors. We try to see how the synoptic details manifest themselves, both on the daily time scales, and here you're looking at monthly time scales, as well as the seasonal time scale itself. And you know, some people like to argue that weekly and monthly and seasonal mean timescale anomalies are generally similar when you start looking at how the atmosphere, when you start looking at the atmosphere from a linear dynamics point of view. But clearly, this monthly mean you see here in February was different than the seasonal mean. And that's a tip-off right there that there's something different going on going into March. And as I just said, with daily monitoring, we were able to catch this with about a 2-week or so lead time, even though the models had not caught it yet. And so what happened in March 2013, the southward shifted jet continues across the Atlantic, strong blocking across the North Atlantic Ocean. This is in the literature. This would be called a negative phase in the North Atlantic Oscillation, and there are reasons why it's called negative. You know, you can do whatever you want with indices, but not only do we have blocking across the North Atlantic, we also have blocking in general across the polar latitudes as well. And this is where you get this notion of the Arctic Oscillation. And notice we also have blocking across the North Pacific. And I can tell you that we were in a base state that at this time was actually strongly La Nina, even though we had a southward shifted jet across the North Atlantic. And that in itself is telling us that there are some behaviors occurring in the atmosphere that are not simple. And more technically, they're called nonlinear dynamics. And we try to catch those things with the GSDM framework. Okay, so what's been going on since then? And I think I got to watch my time here. You know, we had a rather interesting winter, 2012, 2013. A lot of complicated stuff occurring, and you know, there are. If anybody's interested in doing some topics for research, you know, please ask me, because there's a lot of interesting work that can be done this past winter. Okay, the next 3 or 4 slides I'm going to show you are essentially going to be seasonal means for this past summer. And, of course, boundary forcing onto the atmosphere is important, and one of the biggest, if not the most important source of boundary forcing, I don't want to be redundant in my words here, onto the circulation itself, are tropical sea surface temperatures. And just as a bit of an aside here, it's not just the equatorial, central, and eastern Pacific, it's the global tropical oceans have an impact on the circulation, and that's another issue of research that when we start talking about El Nino, Southern Oscillation, you just don't talk about the tropical Pacific. You also got to talk about the Atlantic Ocean and the Indian Ocean as well. Now, this past summer we still had anomalous cool ranging over the central and eastern equatorial Pacific with some anomalous warmth across what we call the Western Pacific warm pool, but these are anomalies. We like to look at totals, and yes, there's some things going on here in the extratropics which start to involve longer time scales and get a little more complicated. You know, for some of you who may be more advanced, you could probably recognize that we also had, on average, a rather robust phase of a negative Pacific decadal oscillation. But again, you know, that's obviously interdecadal variability versus interannual variability when you're talking about El Nino Southern Oscillation versus things such as intraseasonal variability when you're talking about the behaviors we like to look at with the GSDM, where we're linking these, we're trying to link all these time scales together as part of our weather climate linkage framework. Moving on. This is what we saw this past summer, and this is still going on right now with this warm pool starting to shift southward, as it should, with the seasonal cycle. We had a somewhat eastward shifted and expanded warm pool, but if we were going to have an El Nino, this warm pool should already be well to the east. It should be at least to 150, 160 west. It is still west of the date line, not east of the date line. So an El Nino is not looking likely this winter. If anything, the odds, at least in terms of SSTs, actually point toward perhaps a weak cold event, a weak La Nina. Okay, in terms of how the rainfall was responding to the circulation as well as the SSTs, again, you know, the tropics forced the extratropics, but I can also tell you it's the other way around too. There's some complicated stuff, interactions occurring, because you'll notice that the anomalous convection as measured by these colder colors here, these blues and reds, was actually west of where the warmest SSTs were. We actually had suppression across the equatorial dateline where the SSTs were the warmest, which again is a symptom of a La Nina base state. Okay, so seasonal variability. A lot of stuff here. This is the Wheeler-Hendon phase diagram for trying to monitor something called the Mann-Julian oscillation, which is basically a 30 to 60-day behavior of rainfall patterns in the tropics that does impact jet stream behaviors outside the tropics. Klaus Whiten and I derived another global dynamical measure of circulation called the global wind oscillation, this GWO here, which actually encompasses the Mann-Julian oscillation. This index is actually a kinematic or empirical measure within. It's essentially an equatorial measure, whereas this is a global dynamical measure, and as I just said, that encompasses the MJO. And phase diagrams, these are very useful to get into a lot of information in a very short amount of space. This tells us stuff about what's going on both with tropical rainfall variations as well as the circulation. This is the global signal. This is a zonal signal of equatorial rainfall, and here we're starting to look at zonal mean plots in terms of the winds and processes involving the eddies, is what I'm quickly showing down here that are actually derived from the GWO. Now, we're trying to make this global to zonal mean to regional scale linkages, linking global anomalies to regional weather, including extreme weather events. This is where you're going to start getting into the meat of tropical extratropical interactions. This is more recent, about the first week of this month, where we have this wave 01 pattern in the deep tropics, which is actually typical of a La Nina base state in this case. But regardless, wave energy tied to tropical rainfall and circulation patterns in the tropics emanates out and impacts North America. It also impacts other parts of the world. We can apply this framework anywhere in the world, but obviously, in our case, we live here in the United States. And in this case, we were still supporting this ridge across the western half of North America. So, those are the kind of things we look at. Now, in the wintertime, and this was a situation that produced at least 2 devastating ice storms across the plains during, I think this was early December of 2007, as far as the 2007-2008 winter, which was actually a strong La Nina. What happened here, tropical vector forcing with actually a true man-viewing oscillation came out, excited this wave train, and here you can see this a signal here of implied deep layered tropical moisture coming up into the western and central U.S. And Jason earlier showed a schematic of where you get this warm, moist air overriding cold air. Well, that happened big time. I think it was Kansas and Oklahoma that got hit the hardest during these couple of ice storms in about the first 10 days of December of 2007. So let's move on here and start talking about some aspects of this winter. Okay, I haven't got alerted here yet for time, so I think I'm doing all right. These coupled ocean atmospheric models, as well as statistical models and combinations of both, statistical dynamical models. You can do whatever you want to put a model together, and they're actually, many of them are actually pretty sophisticated too. But again, you've got to know what you're using and how these things are built, and what their limitations are, what their systematic biases are, and so forth. Right now, there is a general consensus, let's just say INSO neutral for Nino 3.4, and this is an example of some of the models that are used here. And there is some head of still keeping it cool west and warm east, but as I said earlier, El Nino Southern Oscillation is not just warm, cold, neutral. There's a whole spectrum. And let's just keep that thought in mind as we go forward here. The model forecast, based on what I just showed you quickly for DJF as well as JFM 2014, in some sense, just a continuation of persistence of warm west, maybe near to slightly below normal across the central and eastern U.S., and perhaps a little bit more of a robust cold signal as we get into January and February. But again, these are terrestrial predictions. I would not put a lot of confidence in these in any forecast right now for this winter, because I can tell you, as far as the real time, the weather climate system is extremely noisy right now. So there's a lot of options out there. And this starts to bring into what we look at with our global synoptic dynamic model for subseasonal variability. And I sent Aaron a couple of papers that I'll leave it to other folks' discretion to distribute, where we go into some of the details here. We're showing 4 stages, where the first 2 can be thought of as the La Nina side of what I'm just going to broadly call phase space in terms of the 4-dimensional evolution of the atmosphere. This is an evolutionary framework involving multiple time scales, and stages 3 and 4 would be the El Nino side of phase space. My initial speculation is that I think it is slightly more probable we're going to be shifted more to stage 1, stage 2 this winter. However, the Western Pacific is warm. I think these dark areas are where we schematically show where deep convection is occurring. These large-scale clusters of thunderstorms are occurring. These large-scale sources of tropical heating. I think we will see these things come out a few times during this winter, which will excite these wave trains. And as Jason mentioned, we build these ridges off the west coast and bring cold air in the central and eventually the eastern U.S. I do think you're going to see those episodes this winter, and there's a climatology there. You can say that for every winter. That just says something about predictability there. And notice we do have a few high-impact weather issues that we look at with these various stages. And we do composites. We can do composites on the stages. We can do composites of phases in our phase diagrams. And we do have plans to do efforts that are quite a bit more sophisticated than what you're seeing here. But this is for the GWO, what you're seeing here on the left panel. You're seeing that for the MJO, on the man-juvenile oscillation on the right side, on the right panel here. And as I just said, I think we're more probable to be shifted toward toward warmth in the central and eastern U.S. and the La Nina side of phase space this winter. But if you push me right now, I would be hard-pressed to push a probability distribution either way, because you've got to state these forecasts probabilistically. These are actually signal-to-noise ratio composite anomalies where you can generate PDFs for any points you want. And you notice that these situations where tropical vector forcing does come out more into the western and central Pacific, that can support cold outbreaks into the central and eastern U.S. And I'm surprised that we don't at least have one or two of those that are rather robust this winter. And with that, I thank you for your time and attention, and do welcome questions.
All right, thank you very much, Jason and Ed. That was great, and really, certainly interesting insight as we start preparing for the winter weather. So I live on the East Coast, so I'm particularly sensitive to what might be coming our way. So what I wanted to do this morning is just spend a few minutes talking about how to prepare for winter weather, some things to consider from an emergency notification perspective, and these things pertain not only to winter weather but really any kind of weather, right? Any kind of weather events, hurricanes, tornadoes, etc. But because we're getting ready and thinking more seriously about weather from a winter perspective, here are some things to think about from a preparation perspective. One of the, and these are best practices that our customers have leveraged over the years as they've used the Everbridge system to help them, go through these, various events and make sure that everyone is notified and understands what's transpiring, what actions people should take, etc. And some of these are common sense, right? Well, of course, you want to plan to manage, not just the actual event itself, but the entire life cycle of the event. And we'll talk a little bit about that. A key best practice is, particularly in weather events, is making sure that you have multiple contact paths for the people that you need to reach. Oftentimes with bad weather, for example, with Nemo, a lot of landlines went down. The only way to communicate with people was through, wireless or mobile, etc. And then cell towers can get impacted. So you have to really have as many contact paths as possible for every individual to improve your rate of reaching people. Making sure that your messages are crisp. Leveraging things like social media. There's a whole wealth of information out there, and we'll give some examples throughout the life cycle of an event on how you can actually leverage social media. And of course, testing systems and procedures in advance. These are some things that are common sense, but when you put them all together, really ensure that you can really get the most out of your emergency notification system and leverage and manage events as best as possible. So managing the entire life cycle of a critical event. This is all about preparing messages for roughly 6 phases. The early warnings, how do you alert people to an impending weather event? Assessing risk, what might happen, responding, managing that event, resolution, and then, of course, recovery. One of the things that really helps during these events, and this goes for all phases, the entire life cycle, is being able to leverage more visual intelligence around not only what's happening from a weather perspective and having, the most recent and update weather alerts around, any kind of weather event, but also being able to understand and correlate those weather events with who will be impacted. So having a map-based contact targeting enables you to increase your accuracy understanding, exactly where your constituents are, who needs to be notified, who's available to help. All of those things are better understood in a visual fashion. So we talked about weather alerts. Everbridge leverages WDT for our weather alerts and notifications. So you can see the example here of a blizzard warning. And notice that with the blizzard warning, it gives you a series of polygons of where that warning is in effect. And it also shows you the dots on the map where your contacts are. So, and this is a living and breathing interactive map. You can actually select a polygon and automatically notify people. You can have that notification process fully automated where you don't have to do any selection. Once a warning is issued, those constituents in those polygon areas are automatically notified, or you can, interject some, more manual steps in there depending upon the type of event and how fast you need to respond, etc. So, we do have, over 100 different kinds of weather events and conditions that we monitor and alert on. And again, we talked about confirming, multiple contact paths for the constituents that you have. And this is all about targeting the individual and not the device. Because during any kind of event, modes may be compromised. And being able to, reach people at all costs is key. Just a little bit of best practices around message construction. If you know a certain event is coming, like a blizzard, you have some time to focus on a series of messages trying to prepare and imagine what might happen. And there's just a really easy rule to ensure that your message will be understood by those who are receiving it. And that's called the 3-3-30 rule. A message with 3 short sentences, 3 key messages at most, 30 words at most. And the key thing here is to ensure that you're really telling your recipients what they should do. And sometimes it's important to tell them, that they shouldn't be doing anything. So, not only telling them what proactive measures they should take if you need them to, but also telling them, they shouldn't leave their homes, etc. So what to do and what not to do are both, critical. Social media, from an emergency notification perspective, is really helpful because it acts as a, an additional communication channel, but also you can glean information that helps make your own situational intelligence more, more awareness, and provides you with information that you may not have in order to, make better judgments around what citizens and constituents should be doing. And just some examples of usage of social media. You can see, the city of Boston issuing power outage alerts, etc., and the fact that NSTAR is responding. Those are just examples of how you can get information from, or disseminate information to citizens. Now we'll take a look at some examples of how you can actually leverage social intelligence yourself to improve your emergency mass notifications. And there's really 2 different ways to get that frontline intelligence. The first is social media itself, and that's coming from the general public, Twitter feeds, etc. But the second is to leverage your own frontline intelligence. These are your own staff people who are trusted sources of information, and leveraging a our mobile member application can not only receive messages from you, like, hey, there's a fire warning, but can proactively send you messages, not only, about what's actually transpiring on the front line, but including pictures, etc., so you have a much better idea of what's really transpiring. So that's really leveraging your own frontline intelligence. Some examples of leveraging social intelligence during a weather event and again, this is an example coming from Hurricane Sandy, the ability to leverage social media is important, but you need a means to filter it, right? You know, with 40 million or so tweets coming a day, you don't want to have to look at, you know, all the random tweets that are irrelevant. So Everbridge provides a way for you to really hone in on the tweets that are most important to a particular event to get more intelligence. And the example here from Hurricane Sandy is where, you know, in the days after Hurricane Sandy, when people were trying to return to work, and this included, you know, key staff like hospital, nurses, etc., no one could get gas. And that was becoming an increasing problem. So leveraging social media to find out where you could get gas, where you might want to avoid, you know, real pictures of what the line looks like waiting for gas. I mean, those things help you communicate with, you know, staff people, constituents, etc., in order to know, hey, you know, wow, this person's not going to get into work. I better find a backup, etc. And this is all geotagged, so you understand exactly, you know, where these tweets are coming from. Likewise, you know, after Hurricane Sandy, you can get a sense of the aftermath in areas where, you know, you may not have been able to reach with your own staff. So, you know, this is, you know, left the house for the first time since Sandy hit, and I'm finding some very scary stuff. And, you know, clearly that's not a good thing with the power lines, et cetera. It's a dangerous situation. So gathering as much of that frontline social intelligence as possible helps fill the picture in of what's transpiring. Couple other examples of, you know, this is a winter, right? Being able to understand, you know, what accumulation looks like, how much the drifts are. So, hey, it may be 2 feet, but the drifts are 4 feet. Getting a sense of where the real problem areas are from a drifting perspective. You know, this is other information that you can derive during a winter weather event. So, you know, and finally, you know, these best practices are all, you know, planned in advance. And the more you use the system and the more you exercise any emergency notification system, it improves your frequency of success. So there's some key things to think about from a best practices perspective. You know, data quality is higher for systems that are used more frequently. It's really important to ensure that your data quality is up to date, that you have the right information about your constituents, their contact paths, etc. So the more you test that, the more you understand where you may, you know, have pockets of information that's not as accurate as it should be. You know, condition responses, you know, improve deliverability and confirmation. It's much better to, you know, have practiced these things so you can move through them quickly with confidence, because during the course of an emergency, you know, everyone's stress level is higher. You're a little bit more nervous. Should you really press that button? And being comfortable with the system is key. And again, you know, being able to avoid simple errors, you know, and the recipients themselves, you know, understanding what a message is going to look like, understanding the process, all of those things, you know, will enable your success. And, you know, one of the ways that you can, you know, provide this kind of practice is by using the system for non-emergency use as well. That way people get used to how those messages look, how to respond to them, etc. And they start becoming more familiar and comfortable with the emergency notification platform itself. So those are some best practices that we've learned over the years, over our 10 years. You know, we're not going to spend time going into the details this morning of our product line, but we offer a suite of products. One element of that suite is mass notification. We talk about interactive visibility, which is that social intelligence and where our weather surfaces in a very interactive and living map. and we also have incident management, mobile solutions, etc. We have over 1,500 customers across all these different verticals. So, if you are interested in, pursuing these kinds of solutions, I would encourage you to reach out to Everbridge, and we'll be, happy to address, any of your questions or challenges.
Great. Thank you so much, Claudia. And thank you to all of our presenters. At this point, we have a few minutes left for questions and answers, so we're going to open it up to questions from our audience. So just as a reminder, you may submit your questions by typing a question into the open text field in the questions panel on your screen and submitting to all panelists. And we'll answer as many questions as time allows. If we don't get to your question, we'll try and follow up with you afterwards. So our first question, I think, is for Jason and Ed. So how far in advance is it possible to predict something, even as general as whether it will be a mild winter or a colder winter?
Well, I guess I'll start that one, then Jason can add to it, I suppose. But okay, this is late September. What can we skillfully say about this upcoming winter? One of the key things is to have some form of very strong signal out there to look for. A great example of that was the winter of 97, 98. We had at that time a strong El Nino, a well-pronounced warming of the equatorial Pacific Ocean. And when you have an event of that magnitude, that strongly shifts the odds toward the kind of weather you can expect. This year, we don't have a lot to go on, and a lot of what is going to happen this winter may be driven by just a few relatively short-term events that finally locks in. So that's what makes saying anything intelligent about this winter that is useful difficult. But the only thing I qualify that for is that there is this climate change signal. You all know it as global warming, and in general that has tilted the odds toward warmer, especially across important areas of the eastern U.S. But in situations like this past March, events like that don't care about this climate change.
Yeah, the component I'll add to that answer from Ed is kind of drive home the point. We believe there is enormous amounts of more value to be harvested from the forecast perspective in managing the subseasonal forecast rather than the seasonal forecast. We believe we're actually advancing the science in terms of week 1, week 2, and week 3 prediction for these high impact kind of events a heck of a lot more than we're advancing the science, or than the science can be advanced for monthly or seasonal duration forecast. There's just not enough frequency of coherently evolving low frequency processes to latch onto to extract predictability from on a 3-month lead time basis, whereas there's a heck of a lot more information to glean predictability from in the front 3 weeks for especially high impact events.
Great, thank you. So our next question is for Jason and Ed as well. So the forecast information we went over was obviously very technical. What do you recommend for those of us who are interested in this level of detail but don't have a technical or scientific background?
Oh, don't have a technical background. Well, that's going to be very difficult to answer that in just a few minutes. But what I would recommend is just try to understand just what some of the mechanisms that drive the jet stream. And you can go online, you can Google Google jet stream, and you're going to get a lot of basic descriptions of just what causes the winds to blow the way they do around the world. And then from there, when you want to know more, you can then dig deeper. But that's at least that would be my initial response to that.
Great, thank you.
My response from the Senior VP of Forecast Services level with WDT is more related to our product structure. I think we have done a good job prior to our arrival at WDT as establishing ourselves as subject matter experts in this high-impact weather subseasonal space. Rest assured that while the underlying foundations of the forecast are deeply scientific and incredibly technical, we're damn good at taking that level of information and distilling it down to an actionable level of information for enterprise services. So I guess you could go through the very kind Everbridge folks there if you want to look into more of our product line. But our product line basically gets you down to probabilistic forecasts of warmer than normal or cooler than normal anomalies at the lead time that you're interested in, and it can be as simple as communicating that to blue or red on a map, even though there's a heck of a lot of science behind the blue or the red.
Excellent, thank you. So I think we'll do one more question because we had a great question come through. This one is for Claudia. Can you give an example of the 3-3-30 rule?
That's an excellent question, and I have an example here that was used recently in the Boston Marathon event, and this is around the second phase of the event when the suspect was at large in the Watertown area of Massachusetts. And I'll give you two examples because they're slightly different, and you'll understand why, and it reflects a little bit about the philosophy of what we talked about. So the Watertown itself issued a shelter-in-place message on at 2:35 a.m. As you recall, that's when the suspect first went into Watertown, the shootout occurred, and it says, "This is Detective Connors with the Watertown Police Department. There's an active incident in Watertown. Chief DeVal is advising all East End Watertown residents to remain in their homes. If you hear or see anything suspicious, call the Watertown Police Department at 617-927-6500. So it's telling you, stay at home, call the police if you hear anything suspicious. Meanwhile, as the night progressed and the suspect still was not apprehended, the neighboring city of Waltham, which borders on Watertown, was really concerned. Where is this guy? So they issued a Waltham closed message at 6:30 in the morning that Friday morning, and it says, and it said, from the mayor and chief of police, it is requested that Waltham residents remain in their homes and Waltham businesses to remain closed until the bombing suspect at large has been captured. Follow the news for information. Please do not call the police department. Thank you for your cooperation. So again, it's telling you what to do, stay at home, and what not to do. Do not call the police department. They didn't want to get flooded with calls. And by this time, the news was obviously covering this thing, really from a in-depth perspective. So there's two examples of very crisp messages giving, citizens instructions on what to do and what not to do.
Excellent. Thank you so much. So at this point, I'm very sorry to announce that we've run out of time, but I wanted to thank Jason, Ed, and Claudia for a fantastic session and all of our attendees who were able to join us today. So just a reminder, if you missed any part of the webinar, be sure to look for the slides on everbridge.com/blog, and you'll also receive an email with a link to the recording in the coming days. If you haven't already, please take a moment to follow us on Twitter at Everbridge and join our group on LinkedIn, Everbridge Incident Management and Emergency Notification Professionals. For those of you interested in requesting a demo of the new Everbridge system, please visit everbridge.com/request-demo. And thank you again, all of you, for your participation in today's Expert Insights webinar, Ready for the Storm, WDT's Storm Experts on Winter Weather Preparations. And we hope to see you at a future event soon. Have a great day.
Okay. Bye now.
Thank
you.